All right, so remember that we represent our databases as graphs. So we can represent our databases as graphs. So another type of features that we can obtain for our databases is the features that you can obtain from their graph representations. Okay, and in this section, we are going to look at what are the kind of features that you can obtain from a graph, basically focusing on three types: features about nodes, node features, features about links. Okay, and the link features are basically links about pairs of nodes, not necessarily neighbors. For example, we want to predict whether these two nodes are going to be connected in the future. And graph features, features about the whole graph. Okay, for example, in protein classification. Now, it's important to, well, we assume that G is undirected. Usually, when it is relevant to mention what happens when G is directed, I will do that. All of the techniques generalize. And it's important to understand that we are looking at structural features that are based only on the graph structure. What about the content? What about all of the things that we saw with SQL and so on? Well, that's fine. You can add these. But here we're talking just about the features that you can extract from the graph structure. Okay? So let's talk about node features. The first type of features basically measure how central the node V is with respect to the other nodes in the graph. So one such measure can be the degree. How many nodes does V connect to? Let's see more interesting examples. The betweenness centrality basically says how much V is needed for connecting nodes, how frequently it is that when you go from one node to another in a shortest path, you need to use V. So basically, what the way we define it is as follows: we SP shortest path U prime is a set of all shortest path between U and U prime, and we measure the fraction of shortest paths that visit V. That's SPU V U prime among the set of all shortest path from U to U prime. Okay, and we sum up over all U and all pairs U and U prime basically. Okay, another centrality measure is the closeness. We sum up the distances from V to all of the nodes in the graph. Okay, and since we want to measure closeness, so if this value is large, then we say that it is not close. Okay, so we take the inverse of this value. So that's closeness centrality. Here is another interesting centrality measure that basically shows how linear algebra can be useful in extracting interesting features of graphs. Okay, suppose that this is what the kind of score that we want. Uh, it is normalized. Okay, basically the sum over all of the scores of the nodes, all of the scores of the nodes sum up to one, and that makes sense. We can always normalize any score function. Um, but then we also wanted to have the property that the importance of a node is the sum of the importances of its neighbors multiplied by some constant. Okay, and I'm using 1 over lambda, you'll see next why I'm doing that. Okay, but basically the score of a node is proportional to the scores of its neighbors. Okay, so if our nodes are V1 to Vn, let me denote by S, bold S, the vector of scores. Okay, Si is the score of Vi. So basically, our requirement boils down to saying the following. If A is the adjacency matrix, then what we want is, and you can verify it easily, that A times S is equal to lambda times S. And what does it mean? It means that S is, is an eigenvector for the eigenvalue lambda. Okay? And so we want S to be non-negative, and we want lambda to be positive. And so, the question is, which lambda and S should we use? But even more basically, do they exist? Can we always find such lambda and S? And the answer is positive. And for that, we have the Perron-Frobenius theorem, okay? Which is saying that if we take a matrix with non-negative entries, like the adjacency matrix, um, there is a unique, okay, unique is clear, there's a real eigenvalue that is larger than the others, or at least the others, and not smaller than all of the others in terms of absolute value, so it is non-negative. Its eigenvectors, left and right, are non-negative. And so this basically says, well, we can find such examples. But if A is the adjacency matrix of a connected graph, that's a stronger version of this theorem. If A is the adjacency matrix of a connected graph, then this eigenvalue is greater than zero, okay? And its eigenvector is positive and unique, okay, up to normalization. So if we decide that the sum of the values is 1, then there is precisely one such vector, okay? And basically, the Perron-Frobenius theorem says that for connected graphs, we have a good candidate, right? A natural candidate. Now, if your graph is connected, you can say, okay, take let's compute this score for every connected component and take the unique score for that component. Okay, we call this score the eigenvalue centrality of the node V, and there are well-known approximation algorithms for finding these eigenvalues and eigenvectors, like the power iteration. Okay, so that's on the practical side. If the graph is directed, then we need to use basically this theorem, the Perron-Frobenius theorem, for the strongly connected components. I'm not going to the details of that, but I'll just say that the strong version of the theorem applies to the strongly connected graphs, basically, applies to each strongly connected component. Okay, now the next type of features are the graphlet features, and for that we need a definition of an orbit. So basically, the graphlet features extract features of a node based on the subgraphs that it connects to. Okay, and for that we need the concept of an orbit. So let H be a graph. Okay, it doesn't matter if it's directed or undirected. An automorphism on H is an isomorphism from H to itself. Okay, now if you have an isomorphism from H to itself and a node V is mapped to a node U, then it basically means that V and U play a central role. You cannot really distinguish between them. If you change the names, you cannot know whether we started with V or we started with U. So nodes V and U are similar if there is an automorphism that maps V to U. And this is an equivalence relationship. You can easily verify that. And every equivalence class, okay, set of nodes that are equivalent to each other is an orbit of H. Okay, so now we can define graphlets. So a pattern is a connected labeled graph. It's usually a small one with nodes labeled by their orbits. Okay, every node is labeled by its orbit. And so a pointed pattern is a pattern with an associated orbit. Oh, some node, that we mark as the or some orbit of the graph that we mark as the associated point for this graph. We denote it HO. Okay, H with the orbit O. Now, if G is a graph and HO is a pointed pattern, then we can talk about an HO graphlet of G, which is a subgraph H of V. We denote it, H by H V. And here H is not just a subgraph of G, but rather an induced subgraph. Okay, it is a subgraph that consists of a set of nodes and all of the edges between them. And V is one of these nodes. And importantly, there is an isomorphism phi from H, this graph, to the pattern, small h, where V is mapped to a node with the orbit O. Okay, so this definition may take some time to digest, but basically what it says is that we have here an example of a graph H within the graph G, and the role that V plays in this subgraph is basically the role of that orbit. So let's see an example. This is a list of, and you can find it online, list of orbits up to some sizes or graphlets up to some sizes. These are actually the pointed patterns. Okay, so what do we see here? For each size, we see different graphs with the number of nodes, and the colors represent the orbits. Okay, so these are this is what these figures show, and if you want to transform these into pointed patterns, then you need to mark one of the colors. Okay, for example, here we have 4 colors, and we can say, okay, the black is the orbit, or the orange is the orbit. Okay, and you can also see figures listing the directed graphlets. Okay, so now with this concept of a graphlet, we can define features as follows. We have a list of pointed patterns, okay, H1 to HB, each with its orbit. Okay, for example, it can be the set of all different pointed patterns of between 2 and 5 nodes. Now, we can define this number Ni for the node V, which is basically counting how many occurrences of these pointed patterns there are in the graph. How many H's are such that HV is an HIOI pointed pattern, HIOI graphlet of G. Okay? And again, mapping V to a node of orbit OI. And that gives us a count, and basically from that we can produce a vector of these counts, N1 to NP, each counting occurrences of a pointed pattern. Okay, now we'll use the notation GDV of V, or GDVI of V, to denote this number Ni. And basically this generalizes the degree definition, because the degree definition is a special case when P here is equal 1, and our pointed pattern H1 is simply an H. Okay, and another example is the clustering coefficient. Okay, so the clustering coefficient basically asks how connected are the neighbors of the node. Okay. Now, formally, it is the number of neighbors or edges among the neighbors of V. The number of edges u prime such that both u and u prime are neighbors of V divided by the total number of pairs of neighbors of V. Okay, that's the idea. And so it is not a graphlet directly, but it can be computed or it is determined by graphlet because to get this for the numerator, we use the edge graphlet. For the denominator, oh sorry, for the numerator, we get the triangle graphlet. And for the denominator, we can use the edge graphlet. Okay, so that's another example. Okay. Lastly, I will say that we've seen the Weisweiler-Lehmann algorithm, where basically I'll remind you this is a labeling algorithm. We start by coloring all of the nodes with the same color or labeling them with 0. And then at each iteration, we determine a color that is uniquely determined by the color of the current node V and the structure of colors, the bag of colors of its neighbors. Okay, this is the Weisweiler-Lehmann algorithm, the one WL algorithm. Okay, now one thing we can do is use these colors actually as features, distinguishing different nodes by their structure. And so, you can say, let us take K steps and write down the colors that the node V gets along these different steps. And that can be used as features that tell us something about the structure, how the node V relates to its K-hop neighborhood. Okay. And what do you do? This is categorical. These are categorical values, so you can process them as usual, one-hot encoding, and so on. And that's basically it. So to summarize, we've been looking at several node features. Okay, in terms of centrality, we looked at the degree, betweenness, closeness, eigenvalue, or eigenvector centrality. We looked at graphlet features, okay, based on the counting substructures of the graph, and the Weisweiler-Lehmann features. And next, we're going to talk about link features.